Okay, now I think I'm ready. All right, here we go. So 3.4, we are going to build quadratic models from verbal descriptions and data. All right, so look at, I didn't number these, but this is example number 1. We're going to build a quadratic model. In economics, revenue R in dollars is defined as the amount of money received from the sale of an item and is equal to the unit selling price P in dollars of the item times the number of X of units actually sold. So guys, a company makes money by selling a certain number of products. You take that number of products and you multiply it by the price of that product. That's how you get your company's revenue, okay? The law of demand states that P, the price, and X, the number of units sold, are related. As one increases, the other one decreases. So guys, a lot of times in business, if a company is selling a lot of products, sometimes they can sell at a lesser price because they're selling so many of them. That's how they can still make money. If they're not selling that many, then maybe they have to sell them at a higher price for them to be able to make money, okay? The equation that relates P and X, the price and the number of units sold, is called the demand equation. That's what relates the number of items sold to the price. When the demand equation is a linear equation, then the revenue model is a quadratic function, okay? So we want to be able to maximize the revenue. We want to make this company the most money. The marketing department at Texas Instruments has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators sold is given by this demand equation. So they've given you an equation that relates the number of calculators sold to the price, okay? All right, they want you in part A to find a model that expresses the revenue as a function of the price P. So let's do that first. Again, this is going to be all the flipping back and forth. So we want to be able to write in number 1, part A, we want to write the revenue as a function of the price. All right, they told us the revenue go to get started equation. The revenue is always equal to X, the number of products sold, times P. Okay, they want the revenue to be a function of P. So they want R of P to equal X times P. That means price will be going into this function and the revenue will be coming out. So guys, if they want the revenue to be a function of P, then this equation can only be in terms of P. So we need to get X out and a P in his place. All right, so you're going to need some type of relationship between X and P. But the problem gave us a pre-written relationship between X and P. The demand equation builds you a relationship for X and P. So guys, we already know that the relationship between X and P, X is equal to 21,000 minus 150P. So I'm going to be able to take this piece of information, take X out, put this expression in, and then I'll only have P living inside of this function. Now guys, be careful. Sometimes on homework problems, they might give you this equation, but in order to use it to like sub a certain variable out of the equation, maybe you have to solve it for P so you know what P is equal to in terms of X. So sometimes the demand equation has to be rewritten to be able to get the correct variable in and the correct variable out. Just be prepared for that on the homework in case it happens. All right. All right, so here we go. So we know X is equal to 21,000 minus 150P. So let's plug that in. So now the revenue as a function of P will be equal to not X, but 21,000 minus 150P times P. Now guys, I'm going to distribute that and get it a little bit simplified, and I'm going to switch up the order. So the revenue as a function of price will be equal to, when I kind of backwards distribute, it's negative 150P squared. And then it's going to be positive 21,000P. I just like to have my P squared term in the front. It doesn't matter. If you had 21,000P minus 150P squared, you're all right. It doesn't matter. Okay, nothing's going to get marked wrong. All right, so we did part A. We wrote the revenue as a function of the price of whatever unit of calculator they are selling. Okay, let's go to part B. Part B says, what is the domain? Now, I attached the graph just so we could refer to it. Don't look at it right now. Let's just answer the questions as if the graph wasn't there. All right, it says, what is the domain of R? So guys, the domain R what values of P are you allowed to plug into this function? But it's a little bit more complicated than that. You have to remember that the revenue function started with X times P. Okay, so what would make sense in a real world situation for X and P? Well, if X is the number of units sold, right? Is there a chance that this company created a calculator that nobody bought? Unfortunately, yes. So as far as the domain is concerned, X could be greater than or equal to 0. They're not going to sell negative products, right? So X will either be 0, they sold nothing, or at least 1 or something else, something bigger than 0. They at least sold 1 calculator, okay? And then the price P. Guys, does it make sense that the marketing department of this company said, you know what? I think we have a shot at selling this calculator for $0. Probably not. They're going to at least sell it for some type of money. So it wouldn't make sense for P to be equal to 0 because why would they sell their calculator for nothing? Why are they giving this thing away for free? But it wouldn't make sense for their price to be negative either. So the price just has to be greater than 0. Okay, so this is what we have to consider. We need to make sure that X is always a number greater than or equal to 0, and we need to make sure that P is always a number that is greater than 0. All right, well, our function is written in terms of P, so this guy's good to go. However, we didn't really let X stay in the function. X was this, so it's really 21,000 minus 150P that has to be greater than or equal to 0. All right, and then we'll solve this for P and we'll figure out the 2 conditions that P has to follow. All right, so I'm just going to add my 150 over. I'm going to divide by 150, and I believe you find out it is 140. All right, so as far as the domain is concerned, P has to be a number, I like to read it like this, less than or equal to 140. So the price of the calculator has to stay below or equal to $140. And P has to stay above 0. So if you write this as an interval, P has to be in between 0 and 140. All right. If you write it as a sandwich, then P is in the middle of 0 and $140. Okay. So those are your your one domain. It has 2 conditions. Is everybody okay with that? Yes? Okay, now, if you do look at the graph, because we do have it to refer to, you see how it only goes from 0, but not including him, it's an open circle, all the way to 140, including 140, okay? So we do have the correct domain. Okay, all right, let's go to part C. Oh, I should have lifted that up. Part C says, what unit price should be used to maximize revenue? Well, guys, remember the way this function works. Price goes in as the X coordinate and revenue comes out as the Y coordinate. So they want to know what price should be used to maximize the revenue. Well, if you look at the equation that we wrote to represent the revenue, guys, it's this. It has a negative leading coefficient, which means it's represented by a parabola that opens down. We know the maximum point is the vertex. And the way that vertex works is the price is the X coordinate and the revenue is the Y coordinate. So if they want to know what price maximizes the revenue, they want the X coordinate of the vertex. All right, so all we have to do to find the X coordinate of the vertex is a little negative B over 2A. Right? We'll use our negative B over 2A to find the X coordinate of our vertex. So P will be equal to negative B over 2A. All right, the opposite of B is negative 21,000 divided by 2 times A, which is negative 150. So it's negative 21,000 divided by negative 300. Gone. It's negative 210 divided by negative 3, that's 70. So the price of the calculator that will maximize their revenue is if they sell the calculator for $70. That'll make them the most money according to this information. Is everybody all right so far? Good? Okay. All right, let's go to part D. if this price is charged, what is the maximum revenue? So guys, now you want to plug 70 in to see what revenue comes out. Now we can cheat this one, right? We see that this point, again, I gave you this graph just to reference. We can see that they have the parabola with the vertex labeled at 70, 735,000. So just to save us a little bit of time, in part D, you would have found R of 70. You would have plugged the price of 70 into the function that we wrote in part A, and just a little bit of a spoiler, 735,000 comes out. That's the maximum money they're going to make on selling this calculator. Again, I hope I'm okay in doing that just to save a little bit of time. Okay? All right. Then it says part E. How many units are sold at that price? Well, guys, remember, you do have a demand equation that will relate the number of units sold to the price of that calculator. So if they want to know, okay, well, how many units are sold, then you have to refer to the actual demand equation. If we sell this calculator for $70, what will be the number of calculators that they sold? Because the graph doesn't represent the number of calculators sold. It represents the price and then the money they made, the revenue. So if you actually want to know the specific number of calculators sold, you want to plug that into the demand equation, okay? All right, so let's plug that in. So X equals 21,000 minus 150p. Well, we're going to plug in 70 for P, and you find out, I believe, that, where did I write that down? 10,500 calculators were sold at that price. Okay, everybody hanging in? We're good? Excellent. Okay, then it says to graph R. Now again, graphing R is great. If you wanted to do that right from the get-go, you may have been able to find some of this information out on your graphing calculator. I'm just afraid that if they want simplified exact answers, the graphing calculator will be too much of an estimate and you'll get marked wrong on the My Math Lab. All right, we'll come back to this in a second. Then it says, what price should Texas Instruments charge to collect at least $675,000 in revenue? So guys, think about this. I'm going to write on this picture here. The graph will help me illustrate this. So if you want to make $675,000, right, they want to know at least what price should they be selling the calculator at to at least make $675,000. Well, on the chart, here's 600,000 and here's 700,000. So 670,000 is 75,000 is like up here. So they want to know what price should they be selling the calculator at to make at least $675,000. Well, guys, do you agree that basically, according to the graph, it should be a price in between here and here, right? If you charge or sell this calculator at a price in between any of these prices, then a number from here to here will come out, which will mean at least $675,000 has been made. So first, we're going to find out what makes it actually equal to $675,000, and you should see there's two prices that are going to make it equal $675,000. And then all the prices in between get you more than $675,000. So first, we're going to find out what makes it equal $675,000. Then we'll just put the prices in between them. And then any price in between them gets the job done. All right, so let me go to my paper. So we're going to take our equation and we're going to set it equal to $675,000. What actually makes it equal $675,000? So when does negative 150p squared plus, I believe, 21,000p, am I getting that right? Yep. When does it equal $675,000? So again, this can be done on the graphing calculator. I'm just afraid that if it's not an exact answer, that you're going to get marked wrong. So let's do it by hand first. So guys, it's basically a quadratic equation that you have to solve. I'm going to hope it factors so I don't have to use the quadratic formula. So instead of bringing this to that side because he has a negative coefficient, I'm going to add everything this way. So I'm going to get 150p squared minus 21,000p plus 675,000 equals 0. Okay. Well, we all know factoring is easier when there's no number in front of p squared. So the first thing I'm going to do is see if every single one of these numbers divides by 150 so I can factor it out. Spoiler alert, it does. If you divide 150 out of all this, you're going to get 150 comes out. That's going to leave you with p squared minus, I believe it's, what was it? I don't want 140p, and then plus 4,500. And now you're looking for two numbers that will multiply to 4,500 and add up to negative 140p. So guys, think about it. What multiplies to 45? That could add up to negative 14. 9 and 5. Let's make this work. So we're going to get 150p, and we're going to get p and p. 90 and 50 will make this work. Minus 90 and minus 50 will add up to negative 140 and then multiply to positive 4,500. So that means by setting these factors equal to 0 and using the zero product property, p would have to be 90 or p would have to be 50. So guys, those are the two prices that make this equal the $675,000. So a price of $50 and a price of $90 make it equal. So any price in between them will give you a revenue of more than $675,000. So the answer to the last part is P has to be a price in between $50 and $90, including them. So as an interval, it would look like that. Any price in between 50 and 90. And then as an inequality, it would look like that. Okay. It's a lot, guys. Is everybody okay? Yes? All right. So really quickly, just so you guys are aware, if you use your graphing calculator, because again, our book is enhanced with graphing utilities. They want you to be able to use your graphing utility, your graphing calc. I would just make sure that everybody turns their plot off from the scatter plot diagram that we did, because we definitely don't want any plots on. If you put negative 150x squared, what was it? Plus 21,000x, hit enter. If you go to graph it, my window right now is the standard negative 10 to 10 in all directions. If you look at the graph, guys, we know our domain was 0 to 140, and then they did 0 to like 800,000 on the y-axis. So I'm just going to change my window before I even hit the graph button. I'm going to go 0 to 140. I'm going to count by tens just to make my window a little bit smaller. All right, my max for they went 0, but I like to go a little bit under, so I'm going to go like negative 1,000, and then I'm going to go to 800,000, and I'm going to count by 100, maybe even change that to 1,000 depending on what the graph looks like, and I'm going to graph it. Okay, I'm not loving it for one reason. I want to make sure I go a little bit more below the y-axis, and I think I forgot to make it negative like I normally. Oh, no, I did. Is that enough? Maybe not. Not enough. I'm going to change this so I can go past it. Okay, I like that. So guys, what you could do, if you wanted to use your graphing calculator in part, whatever it was, to find the max, you could have found the vertex by going to the second trace button and asking it to find the maximum. So the maximum 4, all right, you got to get on the left side of your max, move your cursor, hit enter, get on the right side, hit enter, and it says that the max, see how it's like 69.99999? It's not exactly accurate. Oh, we found out that ours was $70, right? And then it was 735,000 was that max. So that's the only reason why I worry about the graphing calculator, is that it might not be that exact value that we're looking for, but at least you could be double checking, and it's a quick thing to do. All right. Another thing was, if you wanted to, you could go back to go back to the y equals. If you put the 675,000 as your second equation and look at the graph, now you could use the intersect button to find the intersection here and to find the intersection there, and then that could get you the 50 and the 90 just as an option to use the graphing utility, okay? All right, here we go. Let's go to the second example now. Okay. This one says, this is number 2. Maximizing the area enclosed by a fence. A farmer has 2,000 yards of fence. To enclose a rectangular field, what are the dimensions of the rectangle that encloses the most area? All right, well, I think we're silly if we don't draw a picture of this. All right, so we have 2,000 yards of fence to make a rectangle. 2,000 total yards of fence. And we're trying to make a rectangle. All right, I'm going to change the wording of this problem up because I'm pretty sure on the homework tonight, it's the exact same problem, but the first thing they ask you to do is to write the area of the rectangle or the enclosure as a function of the width x. Okay, all right, so first of all, we have 2,000 yards of fence to make this rectangle. We don't know any dimensions other than the fact that two sides are always equal, right? These are always equal, and then those are always equal. All right, so guys, first of all, how would you even write the area of a rectangle or find it, right? Everybody agrees area equals length times width, right? They want the area to be a function of x, which represents the width. So obviously we need to get L and W out, and then X is in their place. Okay, well guys, let's go to our rectangle. They said they want the area as a function of the width X. So that's kind of nice because they made that decision for us. You're gonna put X yards of fence as the width, which means it's a rectangle. You have to put the same X yards of fence on the other side of that rectangle. Everybody agree? Okay. All right. Well, guys, we have 2,000 yards of fence to make all 4 sides. We've just used X yards to make these 2 sides. So does anybody know how much fencing we have left? We had 2,000, then we used that amount, and then we used that amount. So does everybody agree? We have 2,000 minus 2X yards of fencing left to make the other 2 sides. Agreed? Well, how do I make sure that these 2 sides get an equal amount of what's left? Cut it in half. So if you divide everything by 2, that's going to leave you with 1,000 minus x. So that means this side is going to use 1,000 minus x yards of fence, and then this side gets 1,000 minus x yards of fence. So now I have the width and the length in terms of x. I can plug them into my function. Everybody good? All right, so now the area as a function of x will be length times width or width times length, x times 1,000 minus x. Distribute your x. I'm just going to rearrange what I get because I have a little bit of OCD and I like mine to be in descending order. So I'm going to get negative x squared and then plus 1,000x. And then there's your function. So guys, the function we wrote is definitely a quadratic function. It has a negative leading coefficient, which means it could be represented by a downward opening parabola. So now we know the vertex is the maximum point, right? And we know that the width goes in as x and the area comes out as y. That's what the ordered pairs are that live on his graph. All right, they asked you to find the dimensions, the length and the width that maximize the area. So guys, we need the x coordinate, the width of this vertex. So it's a little negative b over 2a. So it's going to be negative 1,000, right? The opposite of b over 2 times negative 1. So it's going to be what? Negative 1,000 divided by negative 2, that's 500. So I need the width to be 500, which then if the width is 500, what's 1,000 minus 500? The length is also 500. So it's a square that maximizes the area, 500 by 500 yards. And then obviously if you wanted the max area, what's 500 times 500? Was that 250,000? Okay, and you're done. Everybody okay with that problem? I find these ones to be the easiest ones in the section. Can I just, guys, give you a little bit of a heads up on the homework tonight? There's, I think, a couple of these rectangle problems. One of them, though, talks about making a rectangular enclosure up against a river or a wall. So if that's the case, if you had to make the rectangular enclosure against a river, then technically all you have to enclose are 3 sides. Okay, you don't have to enclose the 4th side. So if the width was X and X, then that just leaves this side to be the 2000 minus 2X. You don't got to cut it in half anymore because there isn't that 4th side that you need to create. So just be careful, because I do think there's a problem like that, and I don't want anybody cutting it in half and then going through an entire problem doing it wrong. Okay? All right, perfect. Let's see if we can at least start the 3rd problem, and then that's probably where we're going to have to stop. All right, the last one, again, it's kind of like another quintessential quadratic word problem, like projectile motion, because anything that is launched, what goes up must come down, and anything that is launched or projected follows the path of a parabola, okay? So it says a projectile is fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal, with a muzzle velocity of 400 feet per second. Guys, I don't know what any of that means, basically. I'm not a physics teacher, but the good news is they've put all of that good information and the picture, and they did all this for us. All right. From physics, the height h of the projectile above the water can be modeled by this quadratic function. Guys, she ain't pretty, but at least they wrote the function for us. Okay. And again, it's 500 feet above the water, so we know it starts at the point 0, 500. It's got a 45-degree angle from the horizontal line straight out, usually where it's 45 degrees from the ground. All right, in this case, because it's starting a little bit higher, the 45-degree angle is just straight across from our line of sight. All right, here we go. Where x is the horizontal distance of the projectile from the base of the cliff. So the x that lives on this graph is the distance that the projectile is from the base of the cliff. So this is when the base of the cliff is 0. Obviously, your distance is 0. You're 1,000 feet away from the base of the cliff. Now your projectile is this high. All right, 2,000 feet away from the base of the cliff. Now your projectile is this high. And then obviously the height is your y coordinate. Okay. A, find the maximum height of the projectile. So guys, they've given you a graph, right? It's the equation that we have is definitely going to be modeled by a parabola that opens down. So the maximum point will be its vertex. So it is a vertex question to find the maximum height of the projectile. That is so not a nice equation though, but we're going to work with it and then we'll plug it into the graphing calculator if we have time. All right, so guys, here it is. H of x equals. I don't like the fact that they wrote x squared in our numerator, so I'm just going to scoot x squared off to the side. So it's negative 32 over 400 squared, guys, is what, 160,000, I believe, for 400 times 400, okay? I'm going to clean that up right now. And then it's plus x and plus 500. Now, you can leave it with the negative 32 over 400 squared. Your calculator can handle that. I just want to do this in case it gets a little bit easier on the eyes. And then I'm going to look to see if this reduces. Does 32 divide into that number? Because then I can make it 1 over a number, and it does. And it reduces to negative 1 over 5,000 times, oh, I forgot the x squared. Sorry about that. And that to me is just a little bit easier to look at, all right? All right, here we go. They want the max, right? So we said this is modeled by a parabola that opens down. We know that the distance from the cliff is x, and we know the height is the y coordinate on this graph, right? They want to know, find the maximum height. So we actually have to find the y coordinate of our vertex. Normally, though, you have to find x, then you plug it in, right? So let's find the x coordinate, because we're going to try and do this by hand first. X equals negative b over 2a. So it's negative 1 over 2 times negative 1 over 5,000. All right, well, 2 and 5,000 reduce to 1 over 2,500. So it becomes negative 1 over 2,500. And then I'll just times by the reciprocal. And you find out that 2,500 feet from the base of the cliff is when it reaches its maximum height. So when X is 2,500 feet, when this projectile is 2,500 feet away from the base of the cliff, it'll be at its highest point. The problem is they want that height. So now you're gonna have to plug 2,500 in to this equation. So if you type it in just like that, it'll do the whole thing for us. So let's plug that into our graphing calculator and see what that maximum height is. (1,750 feet. Is the max height that our projectile is going to reach. Okay, the last thing they ask us to find in this problem, what is the time? 9:33. All right, is how far from the base of the cliff will the projectile strike the water? So guys, if you agree, it started 500 feet above the water, it got projected, and then it's shooting and it's gonna land in the water right there. So, that on the screen. So right there is where it lands and hits the water. So guys, what is its height above the water when it hits it? Its height is now 0. So you have to set the function equal to 0 and figure out when that is. When is it going to hit the water and have a height of 0? All right, so let's set our function equal to 0 and solve. So we're going to set negative 1,000 over 1, negative 1 over 5,000. Okay, now, the way it looks, I would be shocked if it factored. Maybe it does. So what I did just to make myself have easier numbers to look at is I got rid of the fraction. I times everything by negative 5,000 so that I didn't have a fraction to plug in for an A, a B, or a C. So that gave me just x squared, and then it became minus 5,000x in the middle, and then minus 2,500,000. Okay. Now again, you can try factoring it. I don't think it factors, so I went right to the quadratic formula. A was 1, B was positive 5,000, I'm sorry, negative 5,000, and then C is negative 2,500,000. So I'm going to plug that into my quadratic formula. So if they asked you for an exact answer, the exact answer would be 5,000 plus or minus the square root of 35 million. Again, you could probably simplify that. I'm just going to, because I'm running out of time, you might have to simplify the radical, which is fine, over 2. To get your estimated answer, just ask it. What is that? What is 5,000 plus the square root of 35 million equals done divided by 2. So 5,458.04 feet from from the base of the cliff is where it reaches that maximum. Oh, I'm sorry, it hits the water. That's what we were finding, is where it hits the water. If you do the other one, if you do 5,000 minus the square root, you get a negative number, because technically the negative number is back here. It's the number back here where it would have hit the water. So you don't even keep it. That would be your estimated answer if they asked for it. Okay. All right. Again, you could use the graphing calculator. If you wanted to type this equation in and ask it to find the, guys, you have a second trace, you could ask it to find the zeros. It will find the zeros for you with that whole left bound, right bound, if you wanted to do that. Again, I'm just afraid they're going to ask for exact answers, so I just wanted to show you guys how to do it by hand before you do it on the graphing calculator. Same thing, if you wanted to find that vertex, you could have used the maximize button and did the whole left bound and right bound thing again to find the vertex of that parabola. I'm just afraid they're not going to want you to round. Okay. All right. So guys, I'm going to stop there. Did I answer all the questions? Yes, I did. All right. So we're going to stop with the Golden Gate Bridge one.